Hi everyone, our work is on learning when the robot has the wrong hypothesis space. There's been a lot of progress on getting robots to generate trajectories that optimize a pre-specified cost function, typically encoded as a trade-off theta between important features phi of the task. For example, things like distances to obstacles or efficiency. However, with this progress, a logical question that people have started investigating is, what cost function should the robot optimize in the first place? A natural answer is to try to learn this cost from human input. Here's an example of this. The robot starts off with an initial cost function, but as I see it perform the task, I'm pretty unhappy with how high above the table it's carrying the cup. So I push on it to correct it. Previous work has shown how the robot can use such human input to update its belief over trade-offs theta and use it to compute a new estimate, theta hat. The robot can then optimize this new cost function to perform the task in a way that's closer to what the human originally intended. So this works pretty well when the robot knows about all the different things that the person might be caring about. But what if that's not the case? Here I want the robot to stay further away from me, so I push on it. But the robot has no notion of distance from people. Instead, my push brings the robot closer to the table. So not only has the robot not learned to stay far away from me, but it also incorrectly learned to stay close to the table, which is not at all what I wanted. So in this work, we want to be able to detect when the desired cost function is outside of the robot's hypothesis space and avoid making matters worse. When updating the belief over theta, we model people as approximately selecting actions using a Boltzmann noisily rational model. The coefficient beta models how rational or optimal the person is, and is typically fixed. But rather than assuming a beta, our idea is to reinterpret it as a confidence for how well the robot's hypothesis space can explain the human input, and infer that along with theta. Our insight is that the robot should explicitly reason about how well its hypothesis space can explain human inputs, then use that confidence to inform how well it should incorporate them. Concretely, if the robot's hypothesis space is well specified, meaning it knows about what the person wants, our method infers high probability on the correct theta with a high confidence beta. However, if misspecified, the confidence inferred is low for all the hypotheses theta. This allows the robot to know how and when to learn from human inputs. So now as I push on the robot, it infers a low beta, which maps to no longer incorrectly updating the weight on its distance to the table in the cost function. That doesn't mean that the robot magically learns what I want, but it just means that the robot is able to detect that it doesn't understand what I want. Thank you very much.